Hello, folks. Tuning in again. Good to see you. In spirit, if not in body. Today, we're going to do section 5.5 and 9.1, which is about real numbers and their properties, as you can see. Basically, here's the calendar again, not to barrage you with this. But I had scheduled 5.5, 9.1, and 9.2. And having looked at section 9.2, it's kind of involved, so I figured this is probably enough for today. And then I'll push 9.2 to Wednesday's class. Hopefully do 9.2 and 9.3 at that point. Okay? All right. Where we're at this point is having gone through the discussion of real numbers that are rational and irrational. Right? And do remember a couple of things. First of all, we have an abbreviation for a rational number, which is the sort of Gatsby-esque sort of 1920s font R, if you will. When you see something like that, just realize that they're referring to real numbers. It's kind of fancy. It's like Rolls-Royce font, I want to say. Let's see. As for rational and irrational numbers in a nutshell, a rational number is anything that can be a fraction. It may not start out that way, but if it can be converted to a fraction, it's rational. And anything, therefore, that can't be a fraction would be irrational. That is essentially a summary of what has been discussed to this point. Right? Now, there are subcategories of these, and I'll put them here, but beneath rational, there are integers, officially. Integers, spelled correctly. And what you might refer to as regular decimals. You'll see what I mean by that in a moment. Of decimals, there are two types, essentially. There are those that terminate terminating decimals, and those that repeat. They have some obvious pattern to them, like 0.3333 forever and ever and ever. All right. Those are pretty much what you might, although that is, unofficial, regular decimal numbers. I say that because that helps contrast with irrational numbers, which are the other type, if you will, extraordinary decimals. These are non-terminating and at the same exact instant, non-repeating. Which means that they do go on into infinity as a repeater would, like 0.3333 goes into infinity, but they don't have an obvious pattern. All right, famously, there's pi, the square root of 2, and e. Right? These are irrational numbers. Right? And we use those symbols as an abbreviation because it's obviously easier to write a pi symbol rather than write 3.14159, and even then it would be imprecise, because it is infinitely stretching. Right? Anyhow, when you think irrational, think non-terminating, which means it goes into infinity and beyond, right? And non-repeating as not having a pattern to it. Right? Not the typical pattern of a decimal that keeps showing up, or even pairs of decimals, or even an extremely long repeater. Like 22/7 is a famous, very, very long repeating decimal that has several digits. I want to say it's 0.1288571 repeating, something like that. Once you get to the 1, actually, it would be repeating. Anyhow, your book has kind of a nice diagram, so I'm gonna steal it here and add it to my own. This really gives you more of a feel for these types of numbers being subsets of each other, or one of another. Here's what I mean. This is in your textbook, actually. If you wanted to sort of draw a Venn diagram, I know Venn diagrams are usually circular, but this simulates that. All right. The outermost blue rectangle would just be the set of real numbers, right? Which consists of two things, right? That which is rational and that which is irrational. Let's see. I'm going to put this in here. Rational would be the inside of this, just up to this point, to this edge here. So anything enclosed by this would be classified as rational, and anything that is on the opposite side of this would be irrational. So you would have pi, again, the square root of 2, and e on this side. Rational numbers would be, some things like fractions, 1/4. It's very sloppy, 1/4, right? And negative 0.9 is considered a rational number, right? Because you can convert it to 9/10 and it just has a sign attached to it. Even in a repeater like 0.3 with a bar over it. Mixed numbers, 7.8, 3 3/4, things like that. They're all rational, right? The next subcategory of rational would be the integers. And you remember what integers are. Integers are, they're essentially whole numbers, but they're whole numbers with signs. So you can have negative whole numbers, you can have 0 as one exception, and then you could have positive whole numbers. Right. They are a subset of rational numbers. They could be disguised to look like a fraction. If you had negative 3, you could just make it look like negative 3 over 1. Then a subcategory of those would be, and I know I'm really squeezing this, whole numbers in general. Whole numbers in general are 0 and the positives, basically. Right, not the negatives. The integers would include the negatives. All right. A subcategory of those, even further still, would be the natural numbers. And remember, natural numbers are the kind of numbers that do not include 0. They're called natural because we have sort of an intuition about them. They're the counting numbers, the kind of numbers that you would count with your hand. Well, if you had 0, you wouldn't count it with your hand because it's supposed to be representative of nothingness. So why would you have a symbol for that, But 1, 2, 3, 4, 5 into infinity are natural to us because we have 5 fingers on each hand and 5 toes. Right? They're the counting numbers, right? Anyhow, even natural numbers are a subset of real numbers in general. Right? If you look in your e-text, I stole this diagram because I liked it. I say that people going to the profession of teaching are thieves, right? But if you borrow a good idea here or there, I wouldn't feel embarrassed about that. It's for greater good. Anyhow, let's see. How much you steal this? If you want maybe a better picture of this, and I'll try to make you a photocopy. There's a page in your textbook, 249. All right. That's where I took this from. Right. This other stuff is my own sort of diagram here. Anyhow, natural numbers are the innermost box, all right? Just outside of that is the whole numbers, a subset of integers, a subset of rational, a subset of real, all right? And the irrational numbers are the opposite of this line here, because they can't be a fraction, right? All of this stuff on the inside can. A natural number could be a fraction, a whole number could be a fraction, an integer could be a fraction, a rational number is a fraction. Okay. All right, so what are we doing as far as properties are concerned? I need to draw you another diagram. I may have to get a towel because I don't know, the reds and blacks are a little bit hard to erase today, and they get a spritz here. They write the nicest, and that's why I like to write in red and I like to write in black, but they don't erase. Let's see. Incidentally, my rent is due today, so I think we might have a guest speaker. My landlord, he says he wanted me to, well, I paid it on the 1st, but I usually, like right now I'm standing in my, this stairwell, and there's a closet over here, so I usually put the rent check in the closet. And my landlord said, hey, I'm going to be coming over today. And I said, all right, if you don't mind me, if you hear me talking funny, all right, that's just me doing my job. Better than in the bathroom, right? I think so. Desperate times call for desperate measures, as they say. Hopefully that's pretty clean. All right, good enough. Now, what are we doing? Well, section 5.5 specifically incorporates these properties. Indisputable truths, if you will, of math. Right? There's 3 that are well known. I'll put them here. Right? No doubt you have heard of these. My camera's tilting a little bit. I'll fix it. Right. Commutative property. And associative property. And distributive. Green, don't fail me now. Let's see if that is legible from the perspective of the camera. Oh, looks like it's okay. All right. Distributive. Okay. Now, these 2, the commutative property and the associative property, they have 2 categories, subcategories, if you will, each. The commutative property has a commutative property of addition and a commutative property of multiplication. Okay. Similarly, associative property has an associative property of addition and an associative property of multiplication. And I'll give you examples of each. Distributive property is its own thing, right? There are really, I've seen 2 incarnations of this. Your textbook only refers to one of them. There's the distributive property, they say over addition. In other textbooks that I have seen, they will just describe the same sort of model, but they'll have over subtraction instead. All right, not sure why they left that out. I assume it's strategic. Okay. And then there's this other concept, which is a little alien, which is called closure. Right? And I might just go into that first because it's the newest sort of concept. Closure, right? It's going to be, this is 5.5 really, but they bring it up in section 5.5, and it's really more important in section 9.1, Let's see. All right, let me go through the normal 3 of these. I'm gonna label these with a Roman numeral I here. I want to do these 3 before anything else because they're the most practical. All right, and then although the textbook in section 9.1 mentions closure there, all right, it's not like a sort of a model that you follow. It's more or less a procedure, I would equate it with. So I'm not going to put a Roman numeral on that. All right, let's go through this. If you want to, just draw the information I'm about to give you beneath the diagram that was just here. And keep it all in one place, right? Let's see. Of commutative property. Yeah, do it here as I like to. Commutative. Not that I set the best example always, but in my life, especially as a kid, right, people sort of mispronounce the word, right? They'll say commutative, which sounds like community, right? And I'm sure that they have a root in common, that is commu, right? But it's commutative, all right? And commutative property is basically one of these 2 models, right? You've probably seen in your life, right, something that looks like this. I'm gonna label these as models. A as in anything, plus B as in some other anything that isn't the first one, is equal to B plus A, right? And notice that there are pluses in between. This is the commutative property of addition. Similarly, all right, you'll see the same model, but it will be A times B is equal to B times A. A is in anything and B is in some other anything. Okay. Now, in my own life, I had been taught this, I know, in, I'm going to say 3rd grade, and then again in 4th grade, and 5th grade, and 6th grade, and probably high school. And the teacher would say, well-intentioned, they would say, here, write this down, this is important. And I would go, okay, whatever, you just don't yell at me. And I never really appreciated what it was really getting at, you know. If I did anything in homework, it was more or less not to be yelled at, which is not a good reason to be in school, all right? Or I would do things sort of intuitively, like math, which I still say is a blessing if you have an intuition about something good, all right? But just realize that there's an underlying reason, you know, a legal reason, all right? The commutative property is one of those, all right? What it is essentially saying is this: order doesn't matter. Right? It doesn't matter really if you are just adding. Order doesn't matter if you are just multiplying. You could multiply things in any unique order you want if it is a convenience for you. That's really the benefit of it. And here's proof of that. If you had actual numbers to work with, 1 plus 3, you know that if you added them, you would get 4, right? But if I switched the position of these, and put the 3 in the front, and the 1 after it, it would still produce the same result, right? There is a commutative property of addition, so therefore, you can arrange the 2 parts in any order that you like, right? Similarly, multiplication. There is a commutative property of multiplication. So if you had, 2 times 4, right, you can get 8, and if you just reverse the position of these 2 things, 4 times 2, you will get 8 nonetheless, all right? If it is a convenience for you, all right, and that is the bottom line here. You do this not just to, appreciate behold the wonder, of mathematics. It is, elegant, but you do it, you take advantage of this legalese of math, if you will, as a convenience for you, especially if you have several things rather than just two things that are being multiplied. You might find it more convenient to do 2 out of the 3 first, you know, a specific 2 out of the 3 first. All right. Now do notice something though. There is no commutative property of either subtraction or division. And I'm abbreviating it as div and sub. Which means that if there is a commutative property, and all that it is telling you really is that the order doesn't matter, right, for adding strictly or for multiplying strictly. If there isn't a commutative property for subtraction and division, what does that imply? That means order does matter for them. If you reverse the position of things that are being divided or things that are being subtracted, you will get a very different answer in either of those cases. Here's proof of that. Say hypothetically, you had 10 divided by 5, and then I'm trying to make it commutative. I'm just going to take these two things and switch them around. Are they actually going to produce the same quotient? No, they won't, because the position of these, the order in which they arrive, in which they are performed, the operation is performed, right, does indeed matter, right, for subtraction and also for division. In the case of division, 10 divided by 5 is 2, whereas 5 divided by 10 is a half, right? And in spite of their similarity, these are not the same number. They're reciprocals. Reciprocals are not equal. So you put a no smoking cross out through them. Yes, they have the numeral 2 in common, but look at its position. There's a denominator here and more or less a numerator there. That's 0.5 versus whole number 2. Right? If you had a subtraction problem, it might be a little bit more nebulous, but do watch this. If you had 3 minus 2 and 2 minus 3, are they commutative? They are not either, and you see why. All right. 3 minus 2 is 1. 2 minus 3 is the numeral 1, but what would the sign be? All right. It would be negative, right, versus positive. And even again, in spite of some vague similarity, they're the same numeral, they're the same digit, they're the same magnitude, right? They are not the same because they have different signs, right? In terms of a number line, do note where they would be located. -1 would be on the left in respect of 0, and +1 would be on the right in respect of 0, right? These are two different locations. They do not overlap, so they are not equal in spite of any similarity, and hence there is no commutative property, and therefore order does matter for division and for subtraction, respectively. Okay. Then there's the associative property. I wish this red would come off easy. Out, damned spot. You murdered math. The cold-blooded murder of math. Shame on you. Not the most literary person in the world. I do enjoy a good book. I think I like science fiction more than anything. But of all Shakespeare's plays, I've always liked Macbeth. That's where that line comes from. Okay. 2. The associative property. It actually has a model as well. Let me show you the model first. The model looks like this. I like to use, whenever you see models in math, they use a lot of times, I shouldn't say always, but often, they use lowercase letters. So A, B, C. A plus B plus C. 3 things rather than just 2. But to distinguish this from the commutative property, aside from having an extra term, what makes this interesting and unique is the grouping, right, of 2 contents here, and then the shift in the grouping. It has one element in common, one term in common, but they're not identical on both sides. They're different contents, really. Okay. The associative property of addition, and then there is similarly an associative property of multiplication. And depending upon who wrote it, they might opt, in the case of multiplication, actually for a different symbol other than x, right? Especially when they're using letters like A, B, and C. They don't want to confuse the operation with a variable. Anyhow, who's they? You know, the new world order, right? The evil math people, or math overlords, tend to use dots, right? Or sometimes they will simply press 2 things together, maybe both of them in parentheses, each isolated, or not. You know, I like X's. All right. Anyhow, these are the models for addition, for multiplication. All right. And the key element here is that 2 of these out of each 3 are grouped, which means that you would perform those operations first according to the order of operations. Right. Legally speaking, what this is saying is that if it is a convenience, right, grouping doesn't matter really. If you do these first, you're going to get the same answer as if you do these 2 first. Right? The grouping doesn't matter. All right. Therefore, if it is a convenience, do it one way or another. Do whichever. Okay. Now here's an example to illustrate that point. Yeah, I'll put this over here, just underneath the addition model. If you had 3 plus 4 plus 5, and if you had instead the same things in the same order, but they're just grouped differently, you could do if you were strategically doing this for the sake of convenience, all right, you should do the things in parentheses first. All right, so therefore this is really 7, all right, plus 5. All right, and 7 plus 5 is just 12. All right. If strategically you would prefer, for the sake of convenience, to do these 2 first, then that would be 9. And 3 plus 9 would still be 12. Okay. The associative property is probably even more convenient when you get, or I should say, this grouping technique of deciding strategically which things to group is even more convenient when you get to distributed property. Right. We'll do one multiplication and then move on. Suppose you had, I'll use dots in this case, multiplication. 3 times 4 times 5. And essentially the same order, but these are grouped instead. Alright, again, if strategically you have decided to do 3 times 4 first, then you would put parentheses here to emphasize that. This would be 12 times 5, and you would get 60. Right? If in this instance you prefer to do 4 times 5 first, you would get 20, and 3 times 20 is still 60. Right? You see that no matter which way you slice it, thankfully there is an associative property of addition and multiplication at least. Not, again, for subtraction and not for division. Alright, I'm gonna have to get a new eraser, I think. This is getting pretty bad. At this point, it's just kind of spreading muck around my board here. Look at that. It's too bad I couldn't shave a layer off it. I think I might try that later. Not right now. Okay, let's look at the distributed property. I only have time. Okay, good. Right. This is my favorite. Right. If I had to say that I had a favorite property, right? It's a distributed property. Ooh-ah. Okay, here we go. Distributive property. Right? At least the one that is called overaddition. Right? Again, there is another one. I'm not really sure why your textbook does not mention it. Right? It is essentially the same thing. It's just there's a minus in it as opposed to a plus. Right? The model looks like this. A times the quantity B plus C is equal to AB plus AC. Let's see. This means essentially if it is a convenient, if convenient, all right, add first or multiply first. That's really what these two sides are referring to. All right. If you have some content sitting on the outside of the parentheses here, all right, you could distribute it to each of the contents. I like to draw these sort of arcs. All right, there's sort of a visual cue to go, okay, these things are going to be united somehow. All right, the result is on the opposite side here. You could do the content on the outside here times the first on the inside, and then the content on the outside times the second on the inside, and you would end up with these two things. And then, as an afterthought, you would add second, right? So in one instance, you could add first and multiply second. Hope that's not too sloppy. It's a little illegible. You can add first and multiply second, or you can multiply first and add second. Right? Here's an example. Red. If you had 3 hanging on the outside and 4 plus 5. Right. Let us say that you decided to do the adding first and the multiplication second. Right? That is, fixating on the contents of the parentheses and going, oh, okay, I really should, if I were following the order of operations rigidly, I really would do that anyhow. 4 plus 5 is 9. And then it's just a matter of multiplying 3 times 9 is an afterthought, in which case you would get 27, right? Now, if you really used the distributive property, what you could do instead of this, instead of adding first, is legally you could multiply each of the contents first, right? And I'll put them over here, right? 3 times 4 is really 12, and 3 times 5 is 15, right? And if you added those two things, you would nonetheless produce 27, right? And yeah, it's nice to have such freedom, you know. Right? It is sometimes more convenient to calculate in one way versus another. Right. Here's another example where you might try that, right? Maybe not, maybe you have already, you just haven't done it consciously. Let me erase this. That must be why the reason why my markers are not erasing. So erasing is on its way out. So I have to get a new one. Yeah, it's pretty bad. If I have to whiteboard again, I will. Hopefully it's not in too bad a shape. You can see it from the recording. Let's see. Okay, we still in frame here. Yeah, good. All right. Allow me to do an arithmetic problem in front of you. Brute force, all right, and then immediately next to it, arguably more strategic. Suppose that you had this as a problem. All right. 102 times 11. Right. I would like to start by describing how to do this, shall we say, brute force, which is a tried and true means of doing this. There's certainly nothing wrong with it, right? But it is very procedural and kind of involved. All right. And then maybe applying a little more finesse, all right? So, shall we say strategically. In the end, I would not find fault with doing this problem either way. All right, but I'd like to illustrate that you have the option to do it one way or another. I would, if I were in the position of someone teaching 3rd grade math or 4th grade math, I would definitely teach the students how to do something brute force because it works 100% of the time. All right, the strategic method will work 100% of the time too, but it's takes getting used to. All right, so have the method always to fall back on. Just make sure that you emphasize to your students there's often more than one way to do something in math. Okay, now, if I may corrupt your opinion for a moment, right? I have said in the past, and I mean it, that I think that we treat our academic subjects unfairly, right? Well, at least insofar as the United States is concerned. When you're a little kid and they're teaching you how to form your letters, you know, to write them, they give you special paper, right? They give you paper that has lines like this. Right? And they'll say, hey kid, right, listen, you know, when you draw your A's, right, you go up between the solid lines, right? And when you draw your, that's a capital A, when you draw your lowercase a's, you go as far as the dash line, something like that. And it's a skeleton, a scaffold, if you will, for that purpose, right? Not so with math. And there really should be, right? So again, if you're ever in the position of authority, all right, maybe you're a 3rd grade teacher or what have you, give the children graph paper, I say, because even if it seems a little kooky, you know, they go, how anal retentive do you want to be? That you fit a number right into a box. Part of the reason that they make mistakes, as an adult too, all right, is a sloppy handwriting, all right? Neatness helps, and especially in the case of adding, as you'll see, or multiplying, to have things sort of collimated, right? It's a good habit, right, for doing calculations by hand. So, although it might seem a little crazy, right, I'm going to very lightly draw some grid lines. And since my green marker never really is that too robust, I'm gonna sort of do this. Humor me a moment. I'm gonna simulate graph paper. That's how kooky I am. Okay. That's off naturally. Okay. Yes, indeed. I feel that if ever I were to conquer this planet, and someday I just might, you wait and see. All right. First order of business. Everybody gets aluminum foil, right? Because that looks futuristic to me, right? You can wear it, whatever, you know. All right. And the second thing is that you get graph paper when you learn math when you're in 3rd grade. It's a good plan. All right. Right about now, I know what you folks are thinking. Slowly losing his mind if he didn't have it already. All right. Whatever. Be cheerful. Here. Now, if you were going to do this again, brute force. All right. You take the top number that is longer, and you very anal retentively draw the digits into the boxes. All right. And if you want to distinguish them, I'll put the operation in red here to distinguish it from the letters, the numbers rather. Then put the next number of the factor here, collimate, you know, so that what was in the ones place will line up, what is in the tens place will line up, and so forth. And since this is sort of the ledger, the equal sign is what it would really be, I'm going to emphasize this. Do bear with me. All right, now, again, brute force, doing this the old-fashioned way, graph paper just to make it neat, all right? In the United States, this is the way that we were taught years ago, all right? This times this, all right? You write that there. 1 times 2 is 2, all right? This times this, diagonal now. 0, 1 times 0 is 0, and then this times this, diagonal even further. 1 times 1 is 1, all right? And then, if you have another number, you make a placeholder. So I'm gonna just put a placeholder here, and I'll put it in red just to distinguish it from anything that I actually calculate. Not that that's important, but and then you do the next bunch. Let's see. This number times this number is 1 times 2 is 2 again. All right, 1 times 0 is 0, and 1 times 1 is 1. And at this point, if you've ever done this traditionally, you know that you are adding. And again, I'm going to draw a little ledger here. And since you've taken the time to anal retentively align what is in the ones place with what is in the ones place, and what is in the tens place and what is in the tens place, when you're doing the addition portion of the show here, all right, you'll make sure that you will combine together via addition just the things that you ought, all right? And my argument again is that a little kid has sloppy handwriting, right? So give them the skeleton in the same way that you would give them a special loose leaf that looks like this, so that they form their letters properly, all right? Give them graph paper, right? I don't know why culturally in the United States we don't do that to begin with, but hey, I'm not that important yet. Okay, so then you combine your answers here, right? You add up 2, 2, coincidentally 1, 1, all right? And if you're following good etiquette, group of 3, you put a comma. So 1,122, all right? You know what the answer is. That's brute force, it works. Neatness helps is the point, all right? Now, if you're a little bit more strategic, right, and you're trying to do this a little bit faster, if you've already mastered the fine art of doing it neatly, then what you might do is some incarnation of the distributive property. Apply the distributive property. Right. Even if it starts out backwards, right? So if these are the original numbers, 102 times 11, right? What you would do is break up this larger number into a sum, right? Since the distributive property over addition would be a sum inside parentheses. And then, you have this 11 as the factor on the outside that alternatively you could multiply each of the contents by or do the addition first. In this case, for the sake of strategy, we're going to do the multiplication instead, all right? When you are trying to decide what sum addends to break this up into, what these two terms would be, generally speaking, you want round numbers. So in the number 102, there's plenty of choices to go for, right? But a convenient choice would be something that incorporates a nice round number like 100, right? And then the other addend, the other term here that you would have to use is the innocuous Arabic numeral 2, right? What could be more harmless than that, right? Right. Now, yes, normally distributive property has the factor up in the front, but it doesn't matter where it's located, whether it's on the back of the parentheses or in the front. I'm just going to try to conform myself a little bit more to the model for the sake of consistency, all right, for no other reason than that. Okay. So let's say that instead of brute force, instead of doing this addition, we're doing the opposite of addition, which is basically subtraction, really. Strategically, not factoring, that would be multiplication, but breaking this into its two addends. A nice round number and a small whole number, all right? Then you can employ some mental math skills, right? So for example, right, if the distributive property is true, and we know that it is, this outside content would be multiplied independently to each one of these inside contents. You'll get the same answer as if you did it this way, right? The mental math skill that is very handy, right, of when you're multiplying by something with zeros, a round number if you will, all right, is that you really just can ignore the zeros, all right? What's 1 times 11, all right? 11, right? 1 times 11 is 11. How many zeros are there? 2. As an afterthought, you attach the 2 zeros, all right? Super easy, right? Then it's 11 times 2, and I'm not saying it's that commonplace anymore, but a good habit is to get the children to memorize their multiplication tables up to 12 times 12, right? 11 times 2 is 22. Again, the one thing that I've left out here is that this would be cool on graph paper as well, right? Because you should know place values, and that these things added have to lock up. They have to line up appropriately. But then it's the same thing. 1 plus 1 over nothing, you just drag it down. It's just 1. 1 over nothing is just 1. 0 plus 2 is 2, and 0 plus 2 is 2. You get the same answer, right? What is going on here is what you might call mental math skills. Yes, we're incorporating or applying the distributive property in a strategic fashion, right? But when it comes to this point, this isn't even algebra, all right? This isn't even too much arithmetic. It's just going, all right, I'm gonna, as an afterthought, tack on 2 zeros onto 1 times whatever this is. All right, so 1 times 11 is 11, 2 zeros extra is 1100. Okay? In the end, I would tell you, do whatever way you feel more comfortable, all right? But if you're in the position of teacher, at least expose the option. All right, tell your students that you can do it one way or the other. All right, this is often the case in math. There's more than one way to do something. Just keep it in the back of your head. You have choices. All right, it's very important. All right, that's being patriotic too, right? Freedom of choice. All right. I'm starting to wonder if my camera is sinking. I feel like every time I'm recording, I'm getting lower and lower and lower. And soon I'll be on the floor. No teaching from the floor. Okay. That, I feel, is probably the most practical part of this lesson. All right, a lot of the stuff that follows is theoretical. And that's kind of the reason why I wanted to break it up into 2 days. Right. Section 9.2 is kind of a new frontier. All right. Now, as for algebra, all right, let me give you sort of an overview. In algebra, you're inclined to see one of 2 things, all right? One of 2 types of problems. Problems that involve expressions and problems that involve equations. Okay. And what's an expression? Well, an expression is basically a combination of at least 2 out of 3 of these things. It's usually a number, a letter, which would be more appropriately referred to as a variable, right, and some operation between them. So the operation might be adding, subtracting, or multiplying, or dividing, usually, something like that. Or just these 2. Okay. You can have just a number and it would technically be an expression. You can have just a letter and it would technically be an expression, right? But it's usually a little bit more complicated than that. So as long as you meet these 2 criteria, and this is something of an afterthought, right, you have an expression, right? What's an equation? An equation is all of that, but one distinction. All of that in a bag of chips, right? All of that and an equals 2, all right? Even it's the root of the word is equal, right? It has an equal sign in it, right? Why do you care? The reason why you care, especially in algebra, is that identifying it as one or the other will decide what the instructions are, even without being told. To solve, well, first of all, the instruction of simplifying, or to simplify, all right, implies this, all right? The instruction of solve should be reserved for implying this, equations. You solve equations, you simplify expressions. And there are different sets of rules. When you are simplifying expressions, you follow the order of operations. It's fairly intuitive, especially if you have that memorized. All right, PEMDAS, please excuse my dear Aunt Sally. The acronym and the mnemonic. Okay. It isn't lying to you. Like if you see a plus between 2 things, you intuitively are, I'm going to add them, right? However, when you're getting to equations, specifically algebraic equations, what usually is hard for a kid to acclimate to is that it sort of defies the reasoning that they had been programmed to that point. When we see a plus, all right, we go, we gotta add stuff, right? But if it's part of an equation, what you end up doing is you perform opposite operations. And even though it might seem superfluous, right, you do opposite operations, and then to make it legal, you do to both sides of the equal sign. That's what makes it legal. I am fond of saying, because I think it's pithy, right? You can get away with murder in math as long as you're consistent. All right, whatever you do to the bottom of a fraction to augment it somehow, do the same thing to the top of a fraction and everything is cool, right? If you want to start subtracting on one side of an equal sign, do the exact same thing on the opposite side and it's totally legal, all right? So, but this is counterintuitive, right? You perform opposite operations in algebra, right? For the sake of moving things around. Another distinction. When you simplify, all right, you're pretty much sticking with what you have, right? When you're solving an equation, you're moving stuff around. Terms or coefficients, stuff, over equals for the sake of isolating a variable, right? If you move over equals, you do opposite operations. If you're pretty much sticking with one side only, you are just doing the operation that's there, all right? Out of these two things, all right, because equations are a more complicated animal, if you will, organism, think of expressions as being the building block. It is from these that equations are made. Here's how I mean. I regret erasing this, but basically, if you have an expression to generalize, and then you write next to it a second expression, and then you separate them with either an inequality symbol or just a plain ordinary equal sign, they form an equation because expressions are the building block, right? They're the more fundamental piece, if you will. Right? Anyhow, if again, you're just sticking with one side only, you're just cleaning this up, simplifying one side of an expression, you're following the order of operations, right? If you start moving things over equals, right, then you're performing opposite operations to justify that. And you do it to both sides to balance it. The one beautiful thing about algebra, right, is the sort of Zen balancing act that it is, right? The give and take, the symmetry of it. It's elegant. It is a gift. Okay, let me give you an example, and then we'll switch gears here. Let us say that you are just simply simplifying, because we're really not getting into solving equations, not in third grade math, you know. But if a kid really truly understands the fundamentals, they can handle anything, right? As any person could. Right? Just remember this phrase. If you see as an instruction, even one word long instruction, simplifying, right, know immediately what you're dealing with, that this is an expression, and therefore you're going to use the order of operations and maybe some properties. Okay, here's the example. 5 times, put this in better order, x plus 2. Now, we're familiar with the distributive property at this point, and the distributive property over addition says that if you want to add first the contents of the parentheses, go ahead, all right? And if you want to multiply first, that is distributed to each of the contents first, go ahead, and then add as an afterthought, right? When it comes to algebra, you have a little bit more restriction. Your hands are tied, because when you have a letter, a variable added to a number, you don't know what it is, right? So you can't actually add. So in an example like that, you would definitely want to employ the distributive property. Take advantage of what you legally can get away with, which is if I can't add as an option, at least I can distribute, right? 5 times each of the contents. It's distributed to each of those things, you might say. Kind of like a person who hands out leaflets on the corner in New York, all right? 5 times x abbreviated is just 5x, all right? 5 times 2 is just 10. This is admittedly not the most satisfying outcome, because especially in arithmetic, we're kind of used to going, well, the whole objective here is to take something complicated and reduce it to a number. Sometimes, especially in algebra, the best answer that you can give is something that is just simply writing 2 things adjacent to each other, right? 5x and 10, right? And that's the end of it. Until you are given more information, there isn't anything else that you can do. Here's another. If you had, and I want to say recently we're talking about radicals, 5 times 2 plus the square root of 3. These are not like terms. One is a radical and the other is an ordinary number. So although in theory you could convert this to a decimal, right, and then add 2 to it as an afterthought, what you might do for the sake of conciseness, preserving all of infinity, avoiding any kind of rounding, right, is use the distributive property, apply it to both of these things. 5 times 2 is still 10, and 5 times a radical is just the 5 up in front, not in the radical, because the only thing that would allow this 5 to be integrated into the 3 is if it was under a radical itself, and it would have to be the same index, so it would have to be another square root. All right? So again, although it is not the most satisfying answer, that is as much as anybody can do for right now. All right. Here's one other example. So you had this, a radical on the outside of the parentheses, and then one of the contents is also a radical, so 2 here. This, I would just remind you that there is a product rule we had discussed. The product rule for radicals, right, which is if you're trying to multiply them, or if you're trying to do the opposite, which is to factor them. As long as they are the same index, and the index refers to the type of root, you can unite them. this is a square root. If there's no index written here, you would assume it would be 2. Same thing here. So when we get to that point of multiplying by distributing, we can actually combine the 7 and the 2 on the inside of the radical if we want. Right. The result is this. 4 times 7, square root of 7, it is considered good etiquette to put the 4 in the front, all right, since it's not going to be combined with this on the inside. When you're doing square root of 7 times square root of 2, they're the same index, they're the same type of they're the same type of root, they're square roots. You can actually multiply 7 times 2, and you get the square root of 14. Again, not the most satisfying answer, but that, for right now, is the most that anybody could do with it. Okay. Let me wipe down my board, and then we'll go into section 9.1. And then we'll stop. I need to get another paper towel. Now, to discuss section 9.1 in finer detail. Section 9.1 is about groups. All right, that's the title of it. Let me draw you a diagram to summarize. Let me get this out of the way just because I need the space. But we're doing section 9.1. Make sure the camera is correctly in frame. Okay, as long as that is visible. I find that it is good to write something to make sure that I know where the edge is. Okay, all right, and to summarize, all right, there's this concept. There are mathematical systems. This is a new kind of phrase for us. It's a little alien at first, but it's not too big. Right? Mathematical systems. Right? What is a mathematical system? I'm going to write what it is immediately underneath it. Okay. And to make sure that this is legible, so I'll use blue. Okay. What is a mathematical system? It is a set. So if it is a set, in theory, it is something that could be presented to you in fancy braces, right? But it's a specific type of set, right? It's usually a set of numbers and at least one operation. The operation that it typically is either adding or multiplying. OPER is just the abbreviation because I ran out of space here for operation. All right. Something that is a slightly stricter criteria. All right, is a group. More specific type of mathematical system is a group. All right? And a group has 4 criteria that has to be met. So again, I will put this in blue or in alternating colors. All right? Must meet this criteria. Four criteria to qualify as a group specifically. Number 1, the set is closed. I don't know if that's visible. All right. Under the specified operation. So, in other words, by addition or by multiplication, usually. Okay. In order to explain this, I'm going to give you an example. I need a little bit of space, so I'm going to give an example up here. Right? And I'll just erase mathematical system, as you know what we're dealing with, a specific type. Here's an example of something that's a closed group. Or something that has closure. The natural numbers. Remember the natural numbers? The natural numbers are famously abbreviated by the letter N. And if you wrote them in set notation, they'd have a fancy brace. Right? And it would be the type of numbers that you can count, which is excluding 0 specifically. 1, 2, 3, 4, and it goes on forever. So I'm going to put ellipses. The natural numbers are closed by addition. And that means that let's see, how shall I phrase this? If any two of these in the set are added, they produce a natural number. You are closed by a specific operation, right, within the set, that if you involve any two of these together as part of some operation, if they just produce yet another one of their kind, right, another of their type, even if it's the same thing, all right, then it's considered closed. So for example, we'll take any two of these and add them and see if we get a natural number. If I did 1 plus 2, do I get a natural number from adding those things? Indeed, I get 3, which is just another natural number. If I did 3 plus 2, do I get a natural number? Although I didn't write it, indeed I would, because then it would be 5, right? And natural numbers are the numbers that we intuitively know, we intimately know, right? 1, 2, 3, we count, right? And 0 is not involved here. Okay, that's criteria number 1, right? If the set is closed under the operation, and it has to be the operation of adding or multiplying usually. I don't know if that is exclusively true, but it is definitely true for these. Okay. As a side note, addition and multiplication are referred to as binary operations. I'm a little short on real estate here, so what I'm going to do is I'm going to just draw something over here. This is a reference. addition and multiplication are referred to as binary operations. Binary operations because they involve two terms. Two numbers, two terms, two factors, if you wanted to get technical. Whatever is sitting in front of the plus, whatever is sitting after it, 2. Whatever is sitting in front of the multiplication x, whatever is sitting after it. There's 2 of them. Right? The operations are binary. Okay. Getting back to this, our criteria, because there's 4 of them. Let's see if I can squeak this in here. 2. Something is qualified as a group if it has an identity element. What that really means is the number 0 or the number 1, right? That is appropriate, proper for the operation in question. So for example, it might be appropriate to have a 0, right, as an identity. If you're talking about addition, it would be more appropriate to have a 1 included in your set if you're doing multiplication. Right? Reason being, right, there are 2 other properties, which although your textbook doesn't mention them, right, I'm going to right now. This other properties. You intuitively know these anyhow, but I'm going to give a label to them. There are identity properties, and there's 2 of them, and then there are inverse properties. And just as in the case of commutative and associative, there's an identity property of addition, and there's an identity property of multiplication, and also an inverse property of addition, and an inverse property of multiplication to each. All right, here's how they look in terms of the model. Put this in red. Okay. Here's the model. A as in any number plus 0 produces what? If you add 0 to something, it's not going to change the identity of the thing. So what you started with is what you end with. This is the model, if you will, for the identity property of addition, right? And in this case, what is important? 0. 0 is what you would refer to as an identity element that is appropriate or proper for this particular operation. Anyhow, if you have a group, which remember is a set, fancy braces, which has a bunch of numbers in it, if the number 0 shows up in the list, all right, it is appropriate, all right, as long as you're talking about addition. Then there's this. The identity property of multiplication, which has a similar behavior, right? But being that involves multiplication, you have to use the number 1 appropriately. Anything times 1 is the thing that you started with, right? What you start with is what you end with, as long as you multiply by 1, if you're multiplying, right? In this case, what is relevant is the 1. 1 is an identity element. All right, remember, elements are one of the contents of a set. Okay. To further specify, 0 is called an additive identity element. And 1 is called a multiplicative identity element. Let's see. All right, now as far as the inverse property is concerned, again, you really do know this intuitively, but just to give you a model, right? When we're talking about the inverse property of addition, we're talking about something that is the same magnitude but opposite sign, right? Like, for instance, 2 minus 2. Right? What do they produce together? They produce 0 as an outcome. Right? Inverses, additive inverses, which is what these are. Additive inverses produce 0. Okay. Then there's multiplicative inverses. Look like this. A times its reciprocal. They produce 1. These are called multiplicative inverses. A number and its reciprocal, right, are multiplicative inverses. All right, and their outcome is 1 as opposed to 0. Okay. Now 3. Good that we covered that. All right, here's 1, here's 2, and here's 3. Okay. The third criteria is that every element of the set has an inverse under the operation. Every number or every element of the set means it would be encapsulated by fancy braces. Trying to keep a border there. Has an inverse. That's referring to the inverse properties. Appropriate to the operation. Sort of like this. Appropriate, I just briefly wrote the word proper, but I mean appropriate. if the result of combining two elements is that you get 0, all right, as a result, right, then you say that these are inverses of one another, right? And it would be appropriate in that case as long as you're adding to have a 0, right? And that these exist, these coexist, all right? If the result of a binary operation like multiplication is that the identity element 1, all right, exists, all right? All right, each of those elements involved is said to be an inverse, all right, of the other. These are inverses, specifically multiplicative inverses. Okay. All right, now the last criteria that has to be met is this. Right. The set has to be associative. Right. 4. The set, again, is associative. All right. Either of addition or of multiplication. Hey, how are you?
Is there my bothering anybody?
No.
Thank you very much, sir.
Good seeing you.
I'll catch you later. You look well, man. You look good.
Thank you. I'm really squeaking this in. Let's see. Sorry for the mess here. Associative of addition or of multiplication. Whichever is the operation that is in question. There is an even stricter criteria. It is a 5th rule that the thing happens to be commutative also. All right, but it is a very last afterthought. They're truly an afterthought. That's a lot to take in. So your set has to be closed under the addition operation, if that's what you're specifying up in front, that it's involving adding. All right. It has to have an identity element that would be appropriate. In the case of addition, it would be 0. Right. Every element of the set has an inverse appropriate to the operation. So you would see a negative in addition to a positive incarnation of a number, of an element, whatever you want to call it. And the set has to be associative. Right. If you had to check the associative property for every element, it would be kind of cumbersome, so they usually specify that anyhow. Anyhow, let me give you an example, and then we'll end it for today. So I'm kind of going over time anyway, but let me get rid of this. I'm gonna erase that. It's really getting bad. I gotta get a new eraser. Right, Abe, we'll hear about this. Let's see. Let me just summarize that one last bit I alluded to. All right, so we have mathematical systems. All right, any set of elements and an operation. And then we have a slightly stricter criteria, which is they have to be groups, right? Or they can be groups. They meet those 4 criteria. Then there's an extra step, right? If you have a commutative group, has another name as well. Abelian. It's named after a mathematician. An Abelian, Niels Abel it was? Yes. Commutative group. Alright. These are synonymous. Alright. Meets the 4 criteria. And and also is commutative. Commutative. Under the operation that is mentioned or included. So if it's commutative under addition, if you talked about addition to begin with, then fine, right? This is an added step, right? Just checking that criteria. Okay. Now here is an example. Maybe I'll try to do two. All right. Let's see how much time I have here. Here is an example to give you a feel for this. And just remember, in order for something to qualify for a group, all four criteria have to be met, which means that even if one of them punks out on you, it's not a group officially, it's just a mathematical system. All right, let's determine if the system specifically, I'm trying to abbreviate this, the system of whole numbers under addition forms a group. We're going to have to check our four criteria. Right, step by step, and you'll see the intricacies of it as we're going along. All right. That's the procedure basically. Check each criterion. Okay. 1, 2, 3, and if we get to it, 4. First criterion, I believe is singular, to check that. Is the set closed? Under addition. Well, if we're talking about whole numbers, let's start with illustrating what that is. What are the whole numbers? The whole numbers are 0, 1, 2, 3, 4, 5, 6, and it goes into infinity, right? The difference between whole numbers and natural numbers, remember, is that natural numbers start with 1, whereas whole numbers start with 0, right? And does not include the negatives, because that would be the integers instead. Let's see. Anyhow, if it is truly closed, then what that means is that if you add any two, does it produce another whole number? Doesn't have to be a different one, all right? Could be, does it produce a whole number in general as a result of adding? Well, let's take a few and test it out, all right? If you did 0 plus 1, right, does the result of that produce a whole number? Yeah, it produces 1, right? If you did 1 plus 2, right, does that produce a whole number? Yeah, it produces 3, right? Should do several of these really to check, see? if you did, I don't know, 2 plus 6, does that produce a whole number? Yes, it produces 8, right? They're all whole. So the first criterion, all right, requirement is satisfied, right? So far so good. Now we move on to 2. Is there the appropriate identity element? All right, remember the identity elements are either the number 0 or 1. All right, for the operation. In this case, we're talking about addition. All right, well, in the list of whole numbers, all right, I know it's sloppily written here. Yeah, I'll make it a little bit more obvious. These are whole numbers. Zero, 1, 2, 3, 5, 6 is where I went up to. For addition, the appropriate identity element would be 0, all right, rather than 1, because 1 would be more appropriate for multiplication. So therefore, yes indeed, all right, criterion number 2, requirements, whatever you want to call it, is also satisfied. Number 3. Is there, and in this case we're talking about addition, so we want to know additive inverses to adapt it to this problem. Additive inverse for each element. Also, close the door. My neighbor Stan is weed whacking. Okay, now additive inverses, remember, are this situation. All right, in which case they produce 0. All right, but what does that imply? We would have to have negative numbers included in our set. Right, this is basically asking, are there negatives? Right. Got any negatives? And the answer to that is no. The whole numbers exclusively do not, specifically do not incorporate, do not include the negative integers, the negative wholes. All right, so here we hit the brick wall. All right, this criterion, requirements, whatever you have, all right, is not met. So, having gone through the exercise, what could we say? Does it form a group? No! It does not form a group. Right? That doesn't mean it's nothing. It just means that it doesn't meet that specific description. It is simply a mathematical system. Okay? Let's see. Let's try maybe one more of these and then I'll stop. It's kind of tricky, right? Let's see if we can get a commutative group, since that's the stricter criteria. Okay. let's see, determine if the system of real numbers under addition forms a commutative group. So in this case, we're going to have the 4 criteria, and then we're going to check it if it's commutative as an afterthought. All right. So we'll start with 1, 2, 3, 4, and if I could squeeze it in here, I will. Try to confine myself to this much space. 1, is it closed? Under addition, we would need to maybe illustrate some contents of the set, right? If it's real numbers, you know that that's pretty vague, right? Not to rehash this, but let me show you a little drawing here. This is what I was alluding to before. If you were to consider your real numbers, it's everything that is rational and everything that is also irrational. So it's not strict at all. It's very vague, right? You can have negatives, you can have positives, you can have decimals, you can have repeaters, you can have things that are irrational, right? Are they closed under addition? Which means if you add any 2 of these, right, does it produce a real number? The sum. If you added pi to pi, all right, would you get a real number? Both of which are real, right? Yeah, right. If you added the square root of 2 to -5, right, would you get, in theory, a real number? Yeah, right, because both of those things are real, right? This criterion would be met. So you'd say, yes, it is closed under addition, right? You only get more real numbers as a result of adding. Okay. Number 2. Does it have the appropriate identity element, this list? Remember, the appropriate identity element would be either 0 or 1, right? If we're talking about addition specifically, it would be 0 realistically, right? But if we're talking about real numbers in general, again, it's very vague. It's not specific at all. Is 0 incorporated as part of that? Right. Let me show you that diagram once again, just for the sake of analysis. Right. Here's your real numbers, this entire area, all right? Although I didn't write the number 0 up here, all right? A real number is also a whole number, all right? And 0 is part of the list of whole numbers, all right? So it is definitely there, all right? All right? And if you used it to add to anything, if you did pi plus 0, you'd still end up with pi, right? It is proving the identity property of addition. Okay, so yes, this is met as well. Let's see. All right. case, inverses. For each element. Well, if again you're very vaguely talking about the real numbers, all right, that means that the negatives are included as well. A negative anything, a negative square root of 2, all right? You know, a negative square root of 2 plus the square root of 2, all right, are additive inverses, all right? They produce 0, all right? So yes, that criteria is met as well. All right. Now here's the real question. Is the set associative? And you would have to test a few of them in theory, which you can't do for the entirety of them. It's infinite. All right, try 1 or 2. All right, throw in some random numbers. If you had -1 plus 2 plus 3, all right, would you get the same result if you had this group a little bit differently? Would you get the same result if you did this? Grouping the negative with that? Let's see. If I do 2 plus 3 first, I get 5. -1 plus 5 is 4. If I did these two first, I would get +1. +1 plus 3 is indeed 4. So it is indeed associative. All right. Now the last thing is commutative. All right. Is the set commutative? Again, you can't test all of them. It would be mathematically impossible, but maybe try a couple. All right. If it's commutative, and it would be appropriate for addition specifically. All right. Well, let's say that you had a half plus 10, you know. Would you get the same answer if you added 10 plus a half? All right. Well, 10 and a half is what you would get as a result of adding these two, right, in that order, 10 and a half. And 10 and a half is what you would get as a result of adding these two. So, yes, all right, it is commutative. Yes, it is a commutative group, all right, because it meets all four requirements and the fifth one. Okay, all right. Section 9.1 takes a little getting used to, so do try section 9.1 in My Open Math, right? And you'll basically be right where we are as of this afternoon. Okay. Homework. All right. Do section 5.5 and try 9.1 also. In my lab, My Open Math is my other class, I'm sorry. My lab. Alright, do this through Canvas, please. Alright, that's it. Again, on Wednesday, we'll do section 9.2 for sure. Alright, and I will try to squeeze in 9.3 as well. And if worse goes to worse, I'll just push it to next week. Alright, we have still factored into the calendar or review day, which is, you know, added time. Alright, so I'm not worried about that. Anyhow, please try to do these two sections to keep current. All right, and that's it. I'll talk to you whenever. All right, see you on Wednesday.